Hi, everybody. Today we have Ibrahim Chagroor um, talking about one-loop calculations of neural networks. Ibrahim has been working with Professor James Wells in high energy. Um, Here he is, YouTube sensation. Also, you can get started whenever you want.
All right, thank you, Max, for the intro. And thank you all for coming. So I'm going to be talking about one-loop calculations with neural networks. So just before I start, is my audio okay? Everything is working? You can hear me?
Yeah, looking great.
All right. So let's jump into it. Here's the outline. So we're going to be talking about a short history of particle physics, basically leading up to the standard model. Then I'm going to be talking about Feynman rules and diagrams and how those are used to compute things in the standard model, things like scattering cross sections. And then that's going to lead us into loop diagrams, which is the focus of this talk. And I'll talk a bit about how to compute those. Then I'll introduce neural networks and why we're going to use them as function approximators. Then I'll show an application of neural networks to the example of light by light scattering. And then I'll talk about catastrophic cancellation as a barrier to our current method. Then I'll just point out some future directions and I'll summarize the talk. So it all starts in 1897 with Thomson when he discovered the electron. So this was one of the major discoveries of particle physics. Of course, he got the Nobel Prize for the discovery. And then later on in 1919, we had Rutherford who discovered the proton. Now, he didn't get the Nobel Prize for it, but no worries because he already had gotten it in chemistry. So I'm sure he wasn't sad. Later on, we had the discovery of the neutron by Chadwick. And there was another Nobel Prize given. And then in 1932, we had Hess and Anderson, and they discovered the positron. So the positron is the anti-electron, and it was sort of predicted by Dirac when he wrote down his famous Dirac equation, and he was thinking of combining relativity with quantum mechanics, and the anti-electron sort of kept coming up. So these gentlemen got the Nobel Prize for discovering the positron. Then later on, Anderson again discovered a new particle known as the muon. Now, this time around, he didn't get the Nobel Prize, but I'm pretty sure he wasn't sad because he already got one. Okay, so when he got the Nobel Prize, no one was expecting the muon. They actually initially thought it was a different particle, but they then realized that it was just sort of a heavier version of the electron. It had all the same properties as the electron. It was just heavier. And so that led Isaac Rabi to say, who ordered that? And that they were not expecting the muon. No one had ever predicted that there would be this particle known as the muon, okay? But it was discovered. And so that was interesting to physicists, what's going on here. Later on, we had Yukawa, and he was doing some nuclear theory. And he came up with a prediction that there should exist these mesons, these particles, especially the pi mesons, and he thought they would sort of mediate the strong nuclear force. And he was given the Nobel Prize as well because of his prediction of the mesons. In 1961, we had Murray Gell-Mann, and what Gell-Mann did is he sort of explained how you end up with all these mesons. There's the so-called eightfold way of why you end up with a pattern of different mesons. And then he gave an argument of why there are quarks that would give rise to all these mesons. So if you're familiar with SU3, then Gell-Mann basically thought, oh, SU3, that's how you put it all together. That's how you get everything coming out of quarks. So this was, obviously Gell-Mann got the Nobel Prize for his contributions. Then we have these three gentlemen over here in 1961 through 67. They unified the electric force with the weak nuclear force. So we have Glashow and Salam and Weinberg recently passed away. But what they did is they basically combined the electric and the weak forces, and they predicted the existence of a new force carrier, the Z boson, which is neutral. It's sort of like a photon, except it's massive, but it also interacts with the weak force. So they got their Nobel Prize. And then later on, 1984, the W and the Z were discovered. Well, they were discovered before that, but this was when the prize was given out. So this is not strictly in chronological order. There's some wiggle room here. But so Rubia and Vandermeer got their Nobel Prizes for their discovery of the W and the Z. So far we have Nobel Prizes for electrons, for neutrons, for positrons, for mesons, for quarks, and now bosons. So there's all sorts of particles that are being discovered in the 20th century, and a lot of Nobel Prizes are being given. And if you even go closer to us right now, 1990, the quarks were discovered. So deep and elastic scattering experiments were happening, and what you ended up with was Friedman, Kendall, and Taylor discovered that there was strong evidence for the existence of quarks, and they got their Nobel Prize. Even more recently, the tau and the neutrino Nobel Prizes were given for Martin Pearl and Frederick Rines. So now we have new particles on the scene, like the tau, which is an even heavier version of the electron. So it was the electron, then the muon, and now there's the tau. And then you also have the neutrinos, which are the ghosts. They only interact through the weak nuclear force and through gravity. So now we have even more particles to include. And then finally, the most recent huge discovery in particle physics was in 2012. So we had Engler and Higgs, and they came up with the Higgs mechanism back in like the 70s or something like that. And it wasn't until 2012 where the LHC discovered the existence of the Higgs. And that was just a huge deal. It was all over the news. You know, the God particle was discovered, all sorts of things. So once the Higgs was discovered, the standard model of particle physics emerged as sort of complete, quasi-complete. We know it's not complete, but for the most part, this is the pinnacle of particle physics that we have. It's composed of quarks on the top left. You have up, down, charm, strange, and top and bottom quarks. On the bottom left, you have the electron, the muon, and the tau. And you also have the electron neutrino, the muon neutrino, and the tau neutrino. The force carriers, you have the W plus, the Z, and the W minus bosons. You have the gluon, which is responsible for the strong force. And then you have the photon, which is electromagnetism. That's how you're seeing me right now. And in the middle is the Higgs boson, which is the particle or the field that gives all the other particles their masses, if they have one. So this standard model is fantastic. It is so good, in fact, that it's sort of a problem in that it's very good. So the standard model has been tested ever since the Higgs boson at the LHC and other experiments. And every time it seems to get it right. It's hard to break the standard model. But as physicists, we like to find inconsistencies in our theories because usually inconsistencies lead to new discoveries. So to search for inconsistencies, we need to push the standard model to its limit. So this is the big question, is how do I push the standard model to its limit? What do I have to compute in order to get more and more precise predictions and calculations? So here's where I want to introduce Feynman rules and Feynman diagrams, because they are essentially the tools that we use to compute things in the standard model. So every quantum field theory starts out with a Lagrangian. And the Lagrangian is essentially telling you what particles I want in my theory, and it tells you what kind of interactions I will allow. From the Lagrangian, one can derive Feynman rules, and the Feynman rules are essentially ways of converting mathematical expressions into nice pictures using lines and vertices. From the Feynman rules, you can start stitching together lines and vertices, and you would end up with the Feynman diagrams. All right, so let's talk about an example of a quantum field theory. And the one I want to talk about is quantum electrodynamics. It is the quantum field theory that links together light with electrons. Here's the Lagrangian, and it might look scary if you've never seen this Lagrangian before or a quantum field theory, but basically this first term right here is encoding Maxwell's equations. It contains electric fields, magnetic fields, but it's packaged up nicely into a nice form. It's called the field strength tensor. So it contains Maxwell's equations. The second term has a fermion field with another fermion field times a mass. So what this is saying is that I can get energy from mass. This is nothing other than a mass term. It's telling me that there is energy associated with mass. And then you have this last term, and this is composed of this psi is the fermion field. This d mu, you can think of it as a photon field. It's a bit more than that, and that it's the covariant derivative, but you can think of it as the photon field. And this other psi is another fermion field. So this essentially amounts to an interaction term where we're letting fermions and the photon talk with each other. Without this term, fermions don't see photons, photons don't see fermions. Okay, this was why we need this interaction term. Okay, so this is the Lagrangian of quantum electrodynamics. We can move on to the Feynman rules that we get from this Lagrangian. And there's a recipe to do this. I won't go through it, but whenever you take quantum field theory, basically the course is dedicated to understanding how one gets Feynman rules from a Lagrangian. And the way to do it, or not the way to do it, but what you end up with is for external particles, there's lines that are drawn for fermions. And if you have, say, an electron with some momentum p, this is an electron, you would draw an arrow on it indicating the charge flow. And if you had a positron, you would just reverse the charge flow, but it's still moving to the right with some momentum p. Now, the rule here is that you associate a wave function with external particles. So every time you see a line that's external in a Feynman diagram, it's just a wave function. So here's the same thing, it's a wave function. Okay, for photons, it's slightly different in that the wave function of a photon ends up being the polarization of the photon. And we denote photons by wiggly lines. So you can imagine it's moving to the right with some momentum p. Okay, propagators are the particles that end up in the middle of a Feynman diagram. And basically what a propagator tells you is, let's say I have a fermion propagator. It tells you the probability of a fermion moving from point A to point B. And there's a rule associated with it. It's typically the momentum dotted in with the four-dimensional counterpart of the Pauli matrices. And then there's a mass term. And then you have to divide by the momentum squared minus m squared. This is the probability that a fermion would go from point A to point B. And there's an equivalent or a similar propagator for photons, and that's given by the metric, the Minkowski metric. So -1, 1, 1, 1 along the diagonal. And then you have to divide by p squared, which is the momentum. Finally, we have the most interesting piece, which is the interaction. So here, remember, I have a fermion field, I have a photon, and I have another fermion field. That means I have two fermions and one photon. That tells me that the interaction has to be a vertex that has one photon and two fermions. And this is proportional to the electric charge, E. So these are the Feynman rules. From these Feynman rules, we can start stitching them together to make Feynman diagrams. And that's what we're going to do next. So let me move on to some diagrams. Let me draw some diagrams. So let's consider this process, E plus E minus goes to mu plus mu minus. Well, how do I draw that? Well, I need a vertex for the incoming particles. So here's E minus, here's E plus, and I can put a vertex here. And you can imagine that the muons would do the same thing. So there's a muon, mu minus here, and a mu plus here. And there's another vertex right here. So that's how you would draw a Feynman diagram for such a process. You're just following the Feynman rules. You're respecting the vertex rule. Two fermions, one photon. You can draw other diagrams for different processes. Let's say here we have E plus E minus goes to E plus E minus. Well, here you can have E plus E minus combine into a vertex, go into another E plus E minus like this. But there's another way of this happening. You can have the E plus like this. You can have the E plus, you can have the photon, you can have the E minus and the E minus. So this is a different way that the process can occur, but it still respects the Feynman rules. You can also consider other processes like electrons scattering off of photons, and this is known as Compton scattering. I've probably seen before. You can have a photon come in, you can have an electron coming in, and they would give off, you would have this time a fermion propagator, and then at the output you'd have a photon and another electron. So this would be E minus, gamma, gamma, E minus. And then there's different variations of this diagram. So this is how you would stitch together from the Feynman rules to make up Feynman diagrams. Now, each of these diagrams is a long, complicated equation that you can calculate and essentially tells you the probability of such a scattering happening. All right, so what happens if I introduce more vertices? You'll notice that for this E plus E minus goes to mu plus mu minus, I drew just a single diagram like this, and I said E plus E minus goes to mu plus mu minus. And if you count the vertices, here there's 2 vertices. So this goes like E squared, the charge squared. But what happens if I introduce more vertices? Well, how can this happen? Well, imagine I have E plus E minus, they go into a photon, but then this photon splits into an electron-positron pair, and those recombine, and then that photon then goes off and gives you a mu plus and a mu minus. So what happens here is if I count the vertices, I have 1, I have 2, I have 3, I have 4. So this goes like e to the 4th power. What is this saying? It's saying that diagrams like this, which contain more vertices, contribute less because e to the 4th power is a smaller number than e squared because e is less than 1. So there's other ways to end up with these so-called loop diagrams. So you can imagine having E plus send a photon to E minus, and then the E minus absorbs the photon, then they combine, give a photon propagator, and then that photon propagator gets you your mu plus, mu minus. So once again, you have 1, 2, 3, 4 vertices. So this goes like e to the 4th power, which means it contributes less to the total amplitude that you're looking for. Okay, so these are called loop diagrams because of the obvious loop in each of them. So in this case, we have a loop appearing over here. And in this diagram, we have a loop appearing over here. So now the question is, how does one deal with these loop diagrams? What does Feynman tell us to do with these loop diagrams? So here's what you do. Let's assume I have, let me change to black, okay? So let's say I have a photon just whizzing by, minding its own business. You can forget about this process, doesn't really matter now. You can imagine a photon coming in and suddenly it splits into an electron-positron pair, and those two then recombine, and that photon is back to where it was. So a photon coming in has momentum p, and then it splits, but how many ways can you split a momentum p into 2 momenta? Well, there's infinitely many ways you can do it, right? Because nothing's stopping you into splitting it half here, half there, a quarter here, 3/4 there. There's infinitely many ways you can split it. And the way we account for it is we denote an unspecified momentum k, and we denote the other loop propagator by some p minus k. That just tells me that momentum is conserved, but I don't know how the momentum was split. And then these recombine to give you another total momentum of p. So what do I do with this k momentum that's unknown? Well, it could be anything, right? That's what it means to have an infinite number of ways you can split. It could be any momentum. And whenever we have these possibilities of being any momentum, Feynman tells you, well, you have to integrate over all momentum. You have to consider every possible momentum, and you have to integrate over it. And in this case, because we have 2 propagators in the middle, then what you end up with in the denominator is the first propagator, k squared minus m squared. And then you have the other one, which is p minus k squared minus m squared. Now on top, you're going to have a more complicated expression because it includes fermion propagators. It includes this photon that's external, so it has an index mu. So this is a more complicated stuff happening at the top. You might have something like KMU appearing on top. And KMU means I have 4 different numbers, right? Because a 4 vector has 4 different numbers, and each one you have to do an integral. So this is why these things are hard. Doing a loop momentum is really hard. You can imagine a different way this could happen. Maybe another loop diagram to consider is you have this photon being sent from an E plus to an E minus, for example. This is called the electron vertex function. And here, once again, you have an undetermined loop momentum K. And Feynman tells you, well, you have to integrate over all possible K momenta. And then you have to count the propagators. You have to put the right form. So you have K squared minus M squared. And then you have something like K minus P2 squared minus M squared. And then you have 3 of these in the denominator because you have 3 particles in the middle. So you have K minus P2 minus P3 all squared minus M squared. And then there's some complicated expression, some numerator that's very complicated. So good luck trying to do this integral every time it comes up. So every time I give you a process, it's very time consuming, very cumbersome to compute these integrals. Luckily enough, the pioneering work of Giampiero Passerino and Martinez Veltman gives us a systematic way of computing any one loop process that you give me in terms of just 4 integrals that are relatively easier than what you might get from a random process. And these are the so-called tadpole integrals, the bubble integrals, the triangle integral, and the box integral. And what I have here down at the bottom left is, for concreteness, just the box integral d0. And this is the form that it has. And it turns out that it has 12 dilogarithms. And if you imagine computing 12 dilogarithms for, say, 1 million phase space points, that's going to take some time. So we're interested in speeding up these computations, making them easier and faster. So we've reached our first checkpoint here. Let me just quickly review what we've been talking about. So the standard model works very well. It's really good. But as physicists, we like to probe our models. We like to find inconsistencies. So we must push it to the limit. This means that I must compute loop diagrams because loop diagrams are the next correction to the computations in the standard model. Now, the issue is loop diagrams can be slow and computationally expensive. So we need a way of speeding up these evaluations. We need a way of making loop computations really fast so that we don't have to wait too long to get our results. We can generate much data for the LHC and so on. So how should I do this? If I want to speed things up, we choose to interpolate and approximate these slow functions. That's one way of speeding the computations. So I want to take a very slow function to evaluate. I'm going to approximate it, and then I'm going to hopefully compute it much faster. So how do I do that? Here's where neural networks are going to come in. We're going to use neural networks to approximate this box integral that's very slow to evaluate. So what the heck is a neural network? Now, when I say neural network, the first idea that comes to mind is maybe a brain because, well, neural means neurons and a network of neurons. So maybe you're imagining a brain. And how do brains typically work? Well, maybe a brain sees a tree, through its eyes, and then it sort of identifies it. Oh, that's a tree. And then maybe later on you see an image of a dog, and then you would say, oh, that's a dog. So what I'm saying here is that brains take in inputs. Typically, there are physical or chemical stimuli, like light, pressure, sort of molecules coming into your nose. You smell something. And then the brain does some computations. No one knows how it does it. And then it does some output. It gives you some output. That output is usually some action that you do, some feeling that you get, or some thought that you think. So there's an input and then there's an output. So inspired by this, computer scientists thought about, okay, what if I can build something through computers? Okay, it's a black box for now, but I want it to do the same thing. I want it to be able to recognize, for example, that that's a dog. So the issue is with computers, you can't just give it eyes like we do. So instead, you have to give it numbers. Computers work with numbers. So you can imagine replacing an image of a dog by maybe the pixel values of that image. So that's a numerical input. And you would imagine replacing the classification of dog into another number. This time, maybe the number is 2. And what does 2 mean? Well, you look into a dictionary and that tells you 2 means dog, 1 means cat, and so on. You'd have this dictionary. So this is sort of the rough idea that we have. Maybe I want a black box that could do this for me. It could classify numbers into numbers, but in a meaningful way. So the way to do this is through a neural network. So what is this? What are we looking at here? Well, this is a neural network. This is typically how it's represented. And you can look over here. There's the input layer. This is what you're going to put into your neural network. And you can imagine these circles are neurons, like neurons in the brain. And they're all connected through, maybe an axon, for example, to the next neurons in the next hidden layer. And those neurons are connected to the neurons in the next layer, all the way until you reach the output layer. And what you should imagine is that when a neural network is working, I would give it some input, for example, the handwritten digit 6. Of course, to us, we easily recognize it as 6, but how does a neural network know that this is a 6? Well, what it does is, ideally, you'd have the first nodes, they light up, they fire because of the input. And if this is a trained network, you would expect certain nodes to fire a lot because it knows, okay, I've seen this pattern before, I should light up these particular nodes, maybe these not so much, these don't fire as much. And then hopefully these nodes that fired in the first hidden layer, those trigger some nodes in the second hidden layer, and maybe not so much these guys. And hopefully these 3 that light up a lot all converge onto this value right here that lights up a lot. And that hopefully is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the digits from 0 to 9. And the one that lights up the most, hopefully, is a 6. So this is how a neural network works. It propagates the input all the way to the output through this firing process. Okay, so now I want to give you another perspective on how to think about neural networks. So we've seen that neural networks are sort of like brains in that they are composed of neurons and they propagate their information through, but there's a different way of thinking of a neural network. So I want you to look at the diagram on the left. Let me put up the laser pointer. So once again, we have the inputs, then we have the parameters in the middle. So now I don't want to think about hidden layers. That's too complicated. Instead, think of them as dials and knobs that you can twist and tune around to your liking. And just by twisting and tuning those knobs, you can train a neural network to give you this output over here. Okay, what is this? So there's inputs, there's parameters that you can play around with, and there's an output. That's nothing more than a function. A function takes in inputs, it has parameters that you can tune, and it produces an output. So essentially what I'm saying is that neural networks are glorified functions. That's all they are. They're glorified functions, except they have a lot of parameters. So what's the simplest possible neural network you can have? Well, down here you have theta naught plus theta 1 x1. And every single one of you has done this before. This is linear regression. It's the simplest possible machine learning you can have. But of course, you can have a more complicated neural network. So something like this, a tanh of theta naught plus theta 1 times the exponential of x1 plus theta 2 times x2 plus x2. So all sorts of parameters are showing up and all sorts of functions. So this is a obviously more complicated neural network. So this is how I want you to think of neural networks. They're complicated functions with many, many parameters that are tunable. So why neural networks? What's the advantage? Why should we choose neural networks? Well, first, there's the so-called universal function approximation theorem. John von Neumann has been attributed to say with 4 parameters, I can fit an elephant. And with 5, I can make him wiggle his trunk. So what this means is that if I have a lot of parameters, then I can basically fit a function through any points you give me, right? I can fit through anything you give me. And there's a theorem in computer science that says a sufficiently complex neural network can approximate any smooth function to arbitrary accuracy. So this is one reason we like to use neural networks. The other reason is because of their speed. So when you look at neural networks, the computation that happen inside are mostly just linear algebra. They're just matrix multiplications, and you just feed those forward. So nothing too fancy. Now, typically training a neural network can take time, but once you train it, the evaluation after you train it is fast. You can get results very fast. And another advantage is that neural networks can be easily used with GPUs, and that's going to lead to incredible increase in speed. So here's an example. If you have a neural network with 120,000 parameters, sort of a relatively large neural network, you can evaluate 1 million inputs in 2.5 seconds on a CPU. And if you use a GPU, it only takes you 0.06 seconds. So that's incredibly fast. All right, so we've reached checkpoint 2. And here I want to summarize so far what we've been talking about. So I started off by saying the standard model is really good. It works very well, but we want to find inconsistencies in the standard model. We need to push it to its limit. This means that we must compute loop diagrams, but loop diagrams can be slow and computationally expensive. So we need a method of speeding up the evaluation. The method that we choose is neural network approximations and interpolation. So let's apply this method to the example of light by light scattering. Okay. So light by light scattering means I'm scattering off 2 photons off of each other. And if you think about drawing the diagram, you can imagine a photon coming in and another photon coming in, but then you remember the Feynman rule, and it tells you I can't stitch 2 photons into one vertex. So I can't have something like this. This is not allowed in quantum electrodynamics. It breaks all sorts of symmetries. So this is not allowed, but there is a way of doing it. There's a way of getting light to scatter off light if you think of loop diagrams. So the way to do it is like this. Notice that at each vertex, I am satisfying Feynman. I'm telling him, okay, I have 2 fermions and 1 photon. And this is the only way you can get light to scatter off light to first order. So you can count there's a loop in the middle, this is a box, and this goes like e to the 4th power, right? There are 4 vertices. So this is the example we're going to work with. If you imagine the kinematic scenario, you have a photon coming in this way, and a photon coming in maybe the other way, and then maybe they collide in the middle and they sort of go off in different directions. There's an angle that's made by the outgoing photons. And it ends up happening that this diagram, this light by light scattering, depends only on the mass of the inner fermion and this angle theta. So we're going to end up with a function of m and theta. So these are our 2 inputs that we're going to be using. So a quantity that I'll be showing later is the differential cross-section, which is just a measure of how much photons should I expect at each angle. Should I expect more photons at this angle or less photons at that angle? So it's sort of the probability of scattering at a certain angle. And the way you compute it is by adding all the diagrams and you square them and you get your differential cross-section. So using Passerino and Veltman's trick, we can reduce these diagrams into a combination of A0, B0, C0, and D0. These were just the tadpole, bubble, triangle, and box diagrams. So what we want to do is we want neural networks to approximate this D0, this tough function, okay? So how do we do that? Well, let me give you the procedure. Step 1, you're going to generate your training data. And what that means is you're going to generate the inputs and the outputs. So you're going to actually evaluate D0 a lot. You're going to suffer for the first step. So the inputs are going to be the mass and the angle, and the output is going to be the real and the imaginary part of D0. In part 2, you're going to initialize your neural network. So that means you're going to decide how many layers you want, how many neurons you want. You're going to decide what the objective is going to be. You're going to decide what nonlinearities you're going to use. I didn't really touch upon these stuff. They're not really that relevant here. But basically, you have to decide on your neural network architecture. Then in step 3, you're going to train the network. And how this happens is that you feed the training data to the neural network, and then you adjust your neural network parameters at each batch of training points. And then you just keep doing it. You keep feeding in training data, adjusting parameters. feeding data, adjusting parameters until the neural network stops learning. And then once you're done with the learning process, your neural network is now an approximator of D0, but it's much faster at evaluation. So let's look at some of the results for this approximation. So on the left, I have the real part of D0. You have the mass of the inner fermion on the y-axis. You have the cosine theta on the x-axis. And you have the function value on the z-axis. And on the right-hand side, you'll see the neural network approximation of this function. And you can tell that they're the same because if you look down here at the bottom right, it's a large negative value. And if you look down here at the bottom right, it's also a large negative value. So you can tell that these are the same function. But how do you actually test if you did a good job or not? Well, one way is by looking at the relative error. And here it's in percent. And what you'll notice is most of the plot is sort of purple-ish, maybe everything's sort of less than 1% errors until you reach this line over here. And this line basically indicates the function value has crossed 0. So it's not really that big of an issue if you get bad relative error here. That's just because the function has crossed the 0 line. So that's fine. What this is saying is that your neural network is doing really well. We can do the same thing with the imaginary part. You can plot the imaginary part of D0. You can plot the approximation of the neural network, and then you can compute the relative error. And once again, you can see that for the most part, it's purplish. So that's 10 to the minus 1% error or lower, maybe less than 1% at most. So the point is neural networks are doing very well at approximating this difficult function to compute. So now what I want to do is I want to actually compute the total differential cross-section, right? I want to combine all the diagrams, put them all together, and compute the quantity that the LHC would go and measure. And when you do that, on the left-hand side is the actual total differential cross-section. This is what you get without approximations. And on the right is the result that you get using neural networks. And what you can see is that from a first look, it seems to be doing very well, but then you notice that something's happening at the edges. And you can bring out this discrepancy more by plotting the relative error. And what we can see here is that inside the bulk, the relative error is very close to 0. In fact, it almost never exceeds 1% error. But as soon as you go to the edges of phase space, suddenly the error just shoots sky high, starts to increase much higher than 1%. So there's great performance in the bulk, but something's going on at the edges. We're not getting good results with neural networks at the edges. So I spent a lot of time thinking about this. Why is this happening? And it turns out that what's happening is known as catastrophic cancellation or loss of significance or some other name that I'm not familiar with. But basically, here's what's happening. Consider this function, sine x minus x. Suppose I evaluate it at a very small value, like 10 to the minus 5. Well, if you do it to arbitrary precision, the actual answer is this. Okay, it's some really small number, 10 to the minus 14. But now imagine that instead of computing sine of 10 to the minus 5 to arbitrary precision, you actually use an approximation. And let's say your approximation is up to 5 digits, then sine of 10 to the minus 5 is just 10 to the minus 5. And you take 10 to the minus 5 minus 10 to the minus 5, and that's 0. And if you compare 0 to any other number, you're going to get a huge relative error, right? You're going to get it wrong, completely wrong. And that ends up being a problem. The problem is as you move to the edges of phase space, large cancellations are occurring. But since we're using approximations, those cancellations are not happening the way they should. And that's what's leading to the spoiling of our numerical approximation. So what are some ways that one can avoid this catastrophic cancellation? Well, I looked at performing series expansions near the edges of phase space, and this worked out, but the problem is you sort of need many terms in your expansion, and it's also quite slow. It's not really the fast evaluation that we were looking for. The other thing I looked at was training dedicated neural networks near the edges. So what that means is instead of training a neural network for the entire phase space, you just focus on the edge of phase space and you train a neural network just on the edge. And the hope is there you would get a much better performance at the edge. But that also didn't work out because the cancellation was too catastrophic. So the other thing that we considered was a different reduction scheme. Passerino and Veltman, they thank you, you helped us a lot, but it's actually your scheme that's giving us this problem. So maybe we should look somewhere else into a different scheme. So currently we're looking at the Golem reduction scheme. And I wanted to talk more about this for today, but it ended up being quite involved and it takes up a lot of time. So I decided not to include it. So instead, what I'm going to do is I'm just going to summarize the talk for today. So I started off by saying that the standard model is a very good model. It's incredibly good. It has stood all our tests that we throw at it, except maybe a few. So we talked about how if I want to test, I want to push it to the limit, I want to push the standard model to its limit, I need to consider loop diagrams. And that's when I talked about Feynman diagrams and Feynman rules, and we talked about loop diagrams. And I said loop diagrams are hard to compute. If every time I want to compute one, it's a nightmare. And this is where Passerino and Veltman gave us their reduction scheme that simplified the problem tremendously. And we said that, okay, there's this box integral that's really hard to compute. So maybe we can evaluate it faster. We can do an interpolation or an approximation scheme. And that's where we considered neural networks so that we can get fast evaluations. We saw that neural networks are universal function approximators and they're very fast. So we applied it to the example of light by light scattering. But what we saw is that, yes, for the bulk of phase space, there was very good performance. As you move to the edges of phase space, so when the scattering is sort of collinear or when you have really high energy, that's where you start running into issues of catastrophic cancellation. And we saw that catastrophic cancellation spoils our numerical accuracy. And we saw a few ways of how to fix it. And that's where I am currently. I'm trying to work out ways of fixing catastrophic cancellation so that hopefully this relative error plot would be white all over and everything would be fine and we'd all be happy. That's that for this talk. So thanks for listening. Open up for questions. And here's just a few social media links. So thank you.
Okay. Thank you very much, Ibrahim. So I'll stop the recording in case any